Okay, so when we're finding the area between two curves, the important thing to remember is the following thing. I'm going to color code it for a couple of problems. I won't do it for all of them, but you want to remember we're doing the top subtract the bottom. Always top minus bottom. And here's what I mean by that. So let's take a look at this region down here. So here's my region. If I'm making rectangles, so they would be stacked something like this. Okay, and I'm adding up all those areas of the rectangles to figure out the area of this region. All right, this line right here bounds those rectangles on the top, and this equation right here bounds those rectangles on the bottom. All right, so when I find the integral of this, what I want to do is I want to find the integral of my top minus bottom with whatever, and then my bound, so my lower bound and my upper bound, with respect to whichever variable I'm doing it. So if I'm stacking them like this, that's with respect to x. If I'm stacking them horizontally, which we'll see down here on problem 3, I would be with respect to y, but we'll see that when we get down there. Okay, so let's do this problem. So I'm stacking them. They start here at 0, and then go all the way over to here to 6. That's how they're being stacked. So I'm going to do the integral from 0 to 6. And I'm going to use a bracket. I mean, it's the same thing as a parenthesis. It's just sometimes they're easier to see. Because I'm going to do this. I'm going to say top minus bottom. Close. And this is with respect to x. So my top equation is this one right here. And I look at these and I say, okay, which one of those will give me this straight horizontal line at 0? It is g of x. So it's going to be 0. So there's my top equation. Minus my bottom equation, which is x squared minus 6x. And there's my equation. And that's what I would end up actually, if I was going to use a calculator and I wasn't going to do this by hand, I could just type that right into my calculator. It might be nice to simplify this a little bit, just to make it easier on yourself when you type it in. So maybe, that 0 goes away. Distribute the negative. So we've got 0, 6, and then I've got negative x squared plus 6x dx. And we just type that into our calculator. So let's do that now. Let me type it in. And we get 36. So the area of that region is 36. Okay, problem number 2. So same idea. However, so if we look at if I make my stacks here, so there's my rectangles that I'm adding up, right? My top equation, so right here, this is the top of that section, but as soon as I hit this point, this line is now my top bound. So this is my bottom bound, right? And then as soon as I hit that point right there, this is now my top. And this equation is now my bottom. So what that means we're going to have to do is we're going to have to do 2 different integrals. One for this piece and one for this piece. Now, looking at this image, it's pretty clear based on what kind of functions we're dealing with, that these 2 sections are actually going to be the exact same size. So really what we could do is just find the integral for this piece and times it by 2. Or, like I said earlier, you could just write out 2 different equations. So let's see. If I have, so this is my top one. Let's see, this is that curvy one right here. That's going to be this x cubed equation, so f of x. So what I'm going to do, we'll do it down here, the integral from negative 1 to 0 of my top minus my bottom dx, plus the integral from 0 to 1 of top minus bottom dx. Okay, so in this case, in this little one right here, this equation is the top, so 3 times x cubed minus x, okay, and 0 is the bottom. Over on this one right here, my 0 is my top, the top of my bound, or how my region's bounded, right? And my bottom is 3 times x cubed minus x. Okay, so that's one way of doing it, or we could have just gotten rid of this whole thing right here and just stuck a 2 out in front of here. Anyways, we type that into our calculator, and 1.5. So all of that business is, let me get rid of the red, is equal to 1.5. Okay, 0.75 over here, 0.75 over here, and add them together, you get 1.5. All right, let's take a look at, so let's remember that top minus bottom. That's what we're doing on all these problems. Okay, let's take a look at problem number 3. All right, now 3 is a little bit different. We could look at this one of two ways. So we could look at it like this, where my box and my rectangles are stacked like this. Okay, but it could get kind of messy because you notice my top bound, those are bounded on top by that line right there, but then at this point they switch over to this one right here. So I'll just use little dots to kind of show you. They're switching over here. And you know, the bottom is like the same one the whole time, but it's kind of weird on this side. It's the exact same equation for both the top and the bottom. It can get kind of messy. You can do it. You have to get both of these equal to y instead of equal to x, but it's just a mess. So instead of doing it that way, let's erase this. So instead of doing it with stacking it vertically like that is taking a long time. Instead of stacking it vertically, what if we stacked our rectangles horizontally instead? So what I mean by that is like this. So what if they were stacked like this? And I like that a lot because now this right here is bounding them. And it is on the top, and I'll explain why it's the top in just a second. This is the top now. That's where the top of all my rectangles are. And this is the bottom. Whoa, that was a really bad straight line. And that's the bottom right there. Okay? So as I'm doing these ones, I'm writing my top minus bottom, okay, with respect to y. So my equations both have to be in terms of y instead of terms of x, which is nice because they already are. See how they involve y instead of x. And my bounds are also going to be dealing with y. So as I look at this, my little segments here, my little rectangles, are stacked. Here's the bottom. That's where they start, right? They're stacked all the way up to here. That is a y value of -3. And this is a y value of +2. All right? So now it's top minus bottom. Now here's why I know this one's the top. So this is the x-axis, okay? And you'll notice that we're counting +1, +2, +3, +4. So these are the positive direction on the x, negative directions over here. So these, it's kind of like, it's as if you took your normal top and bottom and just rotated it, rotated it 90 degrees. So like this. So now it's like that. Okay, and so that's how you do it when it's with respect to y, and this one's how you do it with respect to x. So this is my top, which it's a parabola tipped on its side, so my equation is going to have a square in it, so that's this guy. So top is 4 minus y squared, and the bottom is y minus 2. And I've got my equation all set up. So now I just have to solve this, and I'll have my answer. So I'll type it in my calculator. Now my calculator doesn't care what the image looked like. I'm just, when I get to this plugging in y's, I'm just going to use the same variable button that I used on the other problem, so the x variable thing. Okay, I'm just going to plug those in. So we type all that into our calculator. 20.833. Remember to always write your decimal answers out to at least 3 decimal places. And on this last one, I mean, it really is 3, 3, 3 after that, right? But right there, you can either truncate it, just cut it off, or if this was a number higher than 5 or higher than 4, so 5 or bigger, I could have rounded it up. Either way would work. So either 20.833 would be the correct answer in this case right there. Okay. All right, let's take a look at problem number 4. Now this one's a little bit different because I don't give you a graph. So you can either try graphing it by hand, or you can use a graphing calculator. I'm going to type it into a graphing calculator. I'm going to use Desmos because I'm lazy. So let me pull it up over here. So let's see, we've got 1/2 x to the third plus 2. So there's my x cubed. Okay. I've also got the equation x plus 1, so right there. And then these, x equals 0 and x equals 2, are vertical lines. So I've got x equals 0 and x equals 2. All right, so it looks like we're looking for, let me zoom in a little bit here. We are looking at this region right here. So they're bounded by the green on the left, the orange on the right, this red piece right here, and that blue piece right there. So this little shaded region right here, okay? So over here, as I write my equation out, okay, it's going to be, and I think this is going to disappear in just a second. So, yep, your top minus the bottom. Looking at the graph, it looks like it would be best to do, over here, to do vertical ones. So with respect to x, okay, our bounds, we are starting at x equals 0 and going all the way over to x equals 2. My cubic function is on top, and this one is on the bottom. So I'm going to put this guy in here, that one minus the bottom, and we're going from 0 to 2. So let's do this. So 0 to 2, this was my top equation based on my graph. This one's the bottom equation based on my graph. And now we just type that into our calculator. And we get, whoa, where did that come from? And we get 2. That's our answer, okay? Make sure when you type it in that you put this piece at least in parentheses, or you distribute that negative through. All right, that's 3 and 4. Let's take a look at 5 and 6. So problem number 5, I'm going to pull up a graph of it. All right, so I guess I'll put it over on this side. You can kind of see it. There we go. So here's my graph. I've got a parabola, and with this equation right here, it looks like it's very similar to problem number 1. Looks like this guy, the parabola is on the bottom. This one's on top. I'm going from 0 to 4. So here we go. We've got, with this guy on bottom, this guy on top. So 0 to 4, top minus bottom. And type that into our calculator. And we get 10.666. So here's what I was talking about earlier, like up here. So I could write that as my answer, or since this goes out 6, forever, I could round it up to 10.667. I would accept either answer, 10.666 or 10.667. Okay, problem 6. Let's graph it. Okay, here's our graph. So we've got our parabola, which is this blue one, and then our line, which is this red one. It looks, so we're talking about this region right in here. So it looks like, once again, we're stacking vertically, so we'll do this in terms of x. Okay, so looks like we're going from an x value of -1 to an x value of 2. So from -1 to 2. Let's do that first. Oops. So let's write our, there it is. So from -1 to 2, top minus bottom, and I've already forgotten which one was which. Parabola is on the bottom, straight line's on the top. So g of x is our top, this one is our bottom. So g of x was our top, 3x plus 3, and this one was the bottom, x squared plus 2x plus 1. Type into your calculator, and you get 4.5. So 4.5 is the area of this little region right in here. Kind of neat. All right, let's move on to the next problem. Okay, so let's take a look at problem number 7. I'm going to actually paste the image of what this looks like over here. So this is the graph of problem number 7. So let me just kind of outline these a little bit. This line right here is y equals x. Okay. This one right here is y equals 2 minus x. And this green one right here is y equals 0. Now, we have some choices we can make. We can stack our rectangles this way in terms of x, right? They're being stacked along the x-axis from 0 to 2, in which case you'll notice my top bound changes halfway through. Now it is symmetrical, so you could do what we did on problem number 2 and multiply by 2, and that's fine. Or you could write 2 different equations. That would work as well. So if I were to do it this way, let's see what it would look like. I'd have the integral from 0 to 2 of, in this case, the top bound is my x, so x minus my bottom bound 0 dx. That would give me this piece right here, that triangle right there, plus, oh, whoops, that shouldn't go to 2. Sorry, that's my fault. That should have only gone to 1, right? Because that's where it changes. So now my eraser's too big. Fix that. All right, so this should have been a 1. So I could times this by 2, or I could figure out what this half is over here, which I want to do because I just want to show you something. So top now is the red one, so 2 minus x, and the bottom is the green one minus 0. Okay. Now doing it this way is a little bit more work. Oh, sorry, from 1 to 2. Okay, and you can you type that all into your calculator. You can do this one in your head probably, since they're triangles. 1 by 1 is 1, cut in half, so that's a half, so that's a half, so the answer is 1. Okay, so that's one way of doing it. You can do it with respect to x, but you can also do this one with respect to y. So let me erase those. And if I did it with respect to y, that means I'm laying them out like this, whoops, horizontally like so, okay? And that makes so I'm going from a y value of 0 to a y value of 1. And the reason why doing it this way is kind of nice is because my top bound stays the same the entire time, and my bottom bound stays the same the entire time. So the only thing I need to do is rearrange both of these equations so that x is by itself. Now that one's already done. This one is just going to be subtract 2 from both sides, so y minus 2 equals a negative x, and multiply by a negative to both sides, so negative y plus 2 equals x. Okay, so this top is negative y plus 2 minus the bottom, which is x, or sorry, y, because it's in terms of y, dy. And if I type that into my calculator, I will also get an answer of 1. Same answer. This one's just in terms of y. This one's in terms of x. Sometimes it's a lot easier to rearrange things, even if you have to change the equations around, to rewrite them in terms of y. And this one is probably pretty easy just to do in your head without even using calculus, but it's a good one to practice on. All right, let's look at problem number 8. Okay, here's what the graph of 8 looks like. Let's pull that over there so we can see it. All right, so we've got, this is our square root graph right here. So this one is our blue graph. This one's the red graph, this line. So if I stack them vertically, so with respect to x, going from 0 to 3, this is going to be my top equation. This one's going to be my bottom equation from 0 to 3. So let's set that up. So we're going to have f is the top, this one's the bottom, and we're going from 0 to 3. Top minus bottom. And we just type that into our calculator. All right, and we get an interesting answer actually. On my calculator I got 1.5, and then I got 5 zeros, 237. Okay. I believe that if you were to do this by hand, the answer you would come up with would be exactly 1.5. The reason why you have this extra little stuff, it's basically, adding very, very, very small number to it, is the algorithm that the calculator uses to calculate this must approximate somewhere, and so that's where you're getting this extra little added stuff. So you got to be aware of that. The answer is just 1.5. And you can recognize it pretty. I mean, you got lots of zeros, and then that's usually a giveaway that that's right. I also typed it into a different calculator, and I got exactly 1.5. So, yeah, the answer is 1.5. Let's look at number 9. Ooh, this one's fun. It's actually set for y's. So let's see what this looks like. Okay, here's the graph of 9. I'm just gonna pull this whole thing over here just so you can see it. So if you're using Desmos, okay, you just have, when you're doing things in terms of y, you just have to make sure you type in x equals, and then you'll get the things. But let's take a look at this. So we've got our parabola here is on the side, and then we've got this line, a linear function right here, or linear equation right here. So if we're stacking these, they're already in terms of y, so that's probably a good indication that I actually want to stack these horizontally like so. Okay, that means we are going from a y value of -1 up to a y value of 2. So those are my bounds, negative 1 and 2. And my top equation, remember this is y, so it's kind of tipped on its side. This line right here is my top, and the parabola is my bottom. So it's going to be y plus 2 minus y squared. So we've got it from, let's see if I remember, it was from negative 1 to 2, and then this one was the top equation. So we'll do y plus 2 minus the bottom equation, y squared dy. And we type that into our calculator and get 4.5. So remember, when you type it into your calculator, you just, instead of putting in y's, you just put in x's and your variable button. All right, okay, this one looks fun. Once again, dealing with y, so we're probably going to be integrating with respect to y. So let's see what this looks like. All right, so get this to fit. Just barely. That's probably, I'll bring it over a little bit. Oh, I know, I can just zoom out. That's smart. Okay, so here's our graph. We're looking at this piece right here. Looks like the state of Minnesota. So if you notice, if we tried doing this with terms of x, it would be a nightmare. We'd be doing them vertically like this, and then we'd have to figure out that piece and that piece separately from it. It would just not be very pretty. But doing this in terms of y is super easy, because as I go horizontally like so, my top function and my bottom function, or my top equation and my bottom equation, never change. This one is always the top, this one is always the bottom. So we are going, our bounds, y values, are going from negative 1 to 2, with our parabola on top and our vertical line at x equals 0, so this guy right here, with the bottom. So it's going to be negative 1 to 2, this minus this. So negative 1 to 2 of my parabola, y squared plus 1, minus my g of y, which is 0. And we type that into our calculator. And we get 6. All right, moving along. Number 11. Cool, almost done. Number 11. Let's figure out what this thing looks like. All right, so this is what our graph would look like. Here's the x-axis. Here's the y-axis, which is one of our bounds. And I'm looking for the region where all 4 of my equations, which in this case are my 4 different colors, make a region. And you can see it right here. It's this piece right here. So as we zoom, so I just want to show you what if you're zoomed out, what the whole thing would look like. And I'm looking for where the 4, where the 4 different equations make a bounded region. So let's zoom in here a little bit. So there it is right there. So if I were to do x, it wouldn't be too bad. I mean, it looks like we change our top bound right here, and our bottom bound would change at this point. So I'd have to do 2 different equations, which is just fine. In fact, let's do that. So here's our graph. I copied down here so I can edit it, so I can kind of draw on it anyways. So if I do it with respect to x, come on, pen work. Get the right color. There we go. All right, so if I do it with respect to x, oh, that's a really bad, it's going to be really hard drawing vertical lines on this, but I'm drawing lines like this, right? So stacking them like this, and you'll see that this is my top bound for a while until I hit that point, and then my top bound changes. So I can do 2 different equations, okay? So I can do the equation from, so integral from 1 to, I guess that's 0. 0, let me just double check my graph. I can't see on that picture. As you can see, oh, I see, it's that y value 1. So, you know, if I were to zoom up, yeah. So we were at, so from 0 to 1, I have my top equation, which is this purple one, which is y equals 10. 10 minus the bottom equation, which is 2, dx, plus the integral from 1 all the way to 5, it looks like, with this blue line now being my top, which is 10 minus x, sorry, 10 divided by x, minus my bottom, which is still 2. So I could do all that, and I could calculate out the answer. And I got 16.094. I'll just double check that in a minute to make sure I did that right. But that's the way you could do it with x. Now you can also do this exact same problem, but do it in terms of y. And like I said, just knowing that you can do it is nice. So you don't have to do it both ways on this one, but that way in future problems you can see which way might be easier. So y would mean that I am coming across like this and stacking my boxes like this. So my lower bound is 2, my upper bound is 10. These are y values. My top equation is this blue one. Now, right now it's in terms of x, so it's y equals 10 over x. I have to get the x by itself. So I'll multiply both sides by x, and then divide by y. So x equals 10 over y. Okay, happily they just switch spots. It doesn't always work that way, so don't try that little shortcut, but it worked out this way this time. So 10 over y minus my bottom bound, which is 0, dy. And now we just type that in. Remember, this is in terms of y. So I'm going to type that into my calculator, and hopefully we get 16.094 again. And I sure did, so that's good. That makes me feel better. So same answer. So anyways, two different ways of doing the same problem. All right, let's look at number 12. Let's see what a picture of this thing looks like. All right, so here's the graph of number 12. So it's kind of a mess. So this blue line right here is our sine function. Okay, this red one right here is our tangent function, and then it's already restricting our domain for us. It's telling us, hey, we're going from negative pi thirds to pi thirds. So I've also drawn those in there too. So that's, let me zoom out a little bit. This is negative pi thirds right here, this purple line, and this blue vertical line is pi thirds. So we're finding the area of this little piece right here and that little piece right here. So we can see that it is symmetrical, so really we only have to find the area of this one and times it by 2, but you could do both of them. Notice that my top equation does change. So on this one, my tangent's the top, sine's the bottom, but at 0, 0, it changes, sine's the top, tangent's the bottom. So let's do this. Let's just times it by 2. So we're going to do go from negative pi thirds to 0. Those are going to be our bounds, with my tangent equation on top and my sine equation on the bottom. So we've got negative pi thirds to 0 with our tangent function on top minus the bottom, 2 sine of x. And there we go. Oh, and I want to times it by 2. Right, that will give me that first little, that'll give me this piece right here, and they're symmetrical, so if I times it by 2, I'll get both of them. And we'll type it in our calculator, and we get 0.6, so 0.6137. So your answer could be 0.613, or it can be 0.614. Either way, I'll accept either one. So there's our answer to that one. So let's take a look at number 13. All right, so here's what it looks like. I've got, oh boy, I wasn't paying attention. This is cosine of x right here. Okay, and this red one is 2 minus the cosine of x. So this one's on top, that one's on bottom. Our bounds, we're going from 0 to 2 pi, so I've got those marked with those vertical lines. So we're going to do 0 to 2 pi, top minus bottom. So 2 minus cosine x minus the bottom, which is also cosine x, and dx. And type that into your calculator. You can simplify this if you want to 2 minus 2 cosine x. It might make it easier to type in. But you get 12.5663. So that would be my answer right there. All right, last problem, number 14. Let's see what it looks like. Okay, here's what our graph looks like. We've got this ugly little function. Right here is our blue line, and then the y equals 0 is the bottom of our function. We're going from 0 to 1. So when we set this up, this is our top equation. That's our bottom equation from 0 to 1. So 0 to 1 top minus the bottom. Plug that into your calculator, and you get 0.316. And we are done.